Okay, so now we're going to do our AC analysis. The first thing we want to do is draw our AC equivalent circuit. Here's our signal generator going in. And in the AC equivalent circuit, basically you take out the DC voltages and currents and you only look at the AC stuff. How you do this is you take the 20 volts and you short it to ground. And then you redraw the circuit with the DC supply shorted, and then you can put the AC in, and then that's the AC circuit. So first thing you'd see is if I bring this to ground, you would see that coming in on the input. This is where we apply V in. So coming in on the input, first thing I would have is a 33 k ohm to ground. Then I have this 100 k ohm here, and although it goes up to the DC supply now, when I do the AC analysis, that DC supply gets grounded. So that 100 k ohms is a resistor to ground. So I've taken care of these guys. Now I got the transistor. What I like to do is put a box in for the transistor as a placeholder. That's a base, collector, emitter. Off of the collector, we can go to there. Off of the collector, I have a 1.5 k ohm between the collector and the DC supply, which is ground. And then normally we'd have a capacitor on here and another load resistor. That capacitor is a short, meaning we also have the load resistor connected here, and there is RC. Oh, don't forget this little guy. Coming off of the emitter, we have a 240 ohm resistor, and then I have another 240 ohm resistor, but this 240 ohm resistor is in parallel with a capacitor. In the AC equivalent circuit, that capacitor is a short, so this one is gone, it's out of the circuit, leaving us with 240 ohms to ground. Then we put in our model for the AC circuit, which has a beta equals 200, and then R prime E. R prime E is that value we find from Boltzmann's constant. We say R prime E equals 0.025 over the DC emitter current, which is 0.025 over 7.06 milliamps, which gives us an R prime E value of 3.54 ohms. So that's 3.54. Okay, so now from this we can solve for Zin. Zin, basically this is the capacitor here. That would be right over here. So this point looking that way is Zin. That would become 33k parallel to 100k parallel to this branch here, which is 201 beta plus 1 times R prime E plus 240, 243.5. You calculate all those values, you end up with a Zin of 16,466 ohm with beta of 200. Z out is the impedance looking back into the circuit. Basically, you consider yourself to be the load, and you ask what is it I'm connected to that's creating a voltage across me. You open current sources. So basically, this would be RC, which would be 1.5 k ohm. Then the final value we're going to calculate is AV, which is the ratio of V out over V in. And to find AV, so AV, what you do is you identify your nodes. V in is over here, so this is V in, including that little piece. This is V out over here. this blue wire. And then you write equations for the voltages based on transistor currents and the impedances in the circuit. So Vn, I would say that, so here's Vn. Basically currents are going back and forth between these 2 points, a little bit comes in there. So I would say IE, the emitter current here goes through these 2 resistors. Oh, excuse me. IE times R prime E plus RE. That's Vn written as a current times a resistance. The out, we do this no load, so we remove the load, and basically it's the current coming out of the collector goes through that resistor. It's IC RC. We substitute in to get this into the same term. We substitute in beta IB and beta plus 1 IB times RC over R prime E plus RE, which is going to be 200. So now we can cancel. 200 over 201 times 1.5K over R prime E is 3.54, RE is that, so 243.5. That comes out to an open circuit, open load gain without the load attached of minus 6.13. It's negative because the output voltage is out of phase with the input.